Hello and welcome back to this second class about trigonometric functions. We're going to see today the graph of two trigonometric functions. Of course, the third one, which is cosine, is going to be in your hands. Objectives for this class. Graph sine function in the coordinate plane with the unit circle values. Graph tangent functions in the coordinate plane with the unit circle values. Conclude the shape of curves of sine and tangent. Graph a complete cycle of sine and tangent function. Okay, this is a short description about what we're gonna do, and it's very interesting because it's something new for you. So I hope you have a lot of attention in this, no distractions. So please, this time to study this topic is so important. It's very important. We're going to start with sine function, and we're going to analyze some of the elements it has. Of course, the values that it has. You already make a list of these values. You already have a knowledge of these values, and I already told you how's the shape of this function. But today we're going to graph it. I'm going to explain you why it's like that. So we can represent sine function like f of x equals sine of x, same as y equals sine of x, because in some books they represent this second notation. Of course, it's at the end is the same. It's just a notation, a way to represent practically the same. So we're going to analyze the values of sine. We're going to conclude the pattern that is following. Sine values in the unit circle are next ones. I think you already know them. There's a unit circle. If you remember, all these values, the y's, are related with sine. So here we have the list, and if you see 0, 1/2, square root of 2 over 2, the square root of 3 over 2, and 1 repeats again, and then repeats but with a different sign. So this situation is already analyzed, and practically what I want to tell you here is that this pattern is making a shape. This is so interesting because many things in math can be modeled like that. And this is what we're gonna do. We're gonna analyze the values that we have in here. So to consider sine like a function, you need to remember that any function requires a set of inputs, the x values, and a set of outputs, what we call y values. Any function works with x and y values. For this specific case, sine or any other trigonometric function work with angles. So what does it mean? It means that the function needs angles to work. That's why you evaluate or replace angles in the value of x. As you can see here, what we have in here, sine of pi 6 is an angle in radians. Pi fourth, pi thirds, pi half, 2 pi thirds, and so on. All these pi values we have in here are radians, are angles, measures in radians. So this is very important you keep in mind. You introduce, in this function, you introduce an angle and then you got a result. The result it's a real number, not necessarily a angle, but this is very important. It's a relationship that starts from angles and then create results. So how are the sine values in the unit circle? Practically, this is what we have. If you want to see it like a table, understanding the values of x we take and the values of y we got. And if you remember the thing of x and y, it's related with the Cartesian plane. And because we want to remember to graph, to conclude the shape of the sine graph and to conclude the shape of a tangent graph, we need to analyze as well this part and be careful with this. Here's where many people get confused. You can evaluate x values, any x value you want, because there's no problem for sine. In tangent, and there are some problems for cosine, which is gonna be your work. You don't have any trouble. You wouldn't have any trouble. So it's very important you understand this part of the presentation right now. So this part of the presentation right now is Understand that you work with some x values and then you get some y values. These x and y values will create coordinates. Those coordinates will help you to understand how is the shape of sine. This is important because what you're doing is modeling a mathematical relation. And practically in many content, this is something that you need to do to describe a situation or to solve a problem. Analyzing the values of sine, if you can see, you get 0, 1 half, which is 0.5, a square root of 2 divided by 2, you can get in your calculator is like 0.70, a square root of 3 or divided by 2 is like 0.86, and then 1 and 0, if you see, you can conclude that practically one of the highest value you can get with sine is 1. This is so important, keep it in mind. And if we continue analyzing, then square root of 3 over 2 is lower than or is less than 1. The same square root of 2 over 2 and 1 half. 0, of course, is less than 1. But then what happened with this other one? This still being less than 1 because they are negative. But if you see, then you have negative 1. But then you don't have anything less than negative 1. So those values are very interesting, inclusively the 0. 1 and negative 1 are telling you that this sine function is not moving more than 1 or less than negative 1. So practically this is working like a roof and this is working like the floor of the function. This is so interesting because right now this function sine of x can give you values like 1.5 or 2.6 with any angle you choose, no matter if the angle is in radians or degrees. I mean, you can try here. I know it's not in the list, but you can try here in your calculator. Just be sure that your calculator is in radians. You can try sine of pi over 8, for example, and you're gonna have a value. I'm gonna tell you which is the decimal value, of course. Sine of pi over 8 gives you like 0.38, and you can continue working or trying. What about pi nines? 0 point something. So you can try with any x value, and my point is that you will not get any value or one value that's gonna be greater or less than negative 1. So keep in mind this important idea that sine is practically sine of x, right? Is practically working between 1 and negative 1, okay? So we're going to continue with the analysis of this. So this is very important. And the other values, that means that the other values are not important. No, they are important because they will tell us how is the shape of sine. So here you have, or here I'm going to list all the points we can create, and then we're going to plot those points in a Cartesian plane. Here you have your first point, x value, always is first at the x and then the y. So the point x comma y is going to be 0 comma 0 in that case. Here you have pi 6 comma 1 half, pi fourth comma square root of 2 over 2, pi thirds comma square root of 3 over 2, pi and a half comma 1, and then you start to go down because then you go back again with square root of 2 over 2, square root of 3 over 2, sorry, then square root of 2 over 2. But if you see, I'm working these x values like the radians I use, I mean the angles I use in order to create that, that shape. So all the points that I will have are in here. Look, all the points that I'm gonna plot are here. Okay, now having this big list of points, if you see there are like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, like 17 points. We're gonna graph in the coordinate planes to conclude the shape of sine function. It's very important we analyze something because this is something you're going to do later when we study the trigonometric transformation of these functions. For example, what's a common denominator right now? If you see, you have 6, you have 3, you have 4, you have 2. I think 6, 3, and 2 have in common the 2 and the 3. There's no any trouble with this ones. And I'm doing this because we want to make the graph of this. What could be a common denominator or a common multiple between 6, 4, 3, and 2? You can get the common multiple between those numbers, and I think the common multiple they can make or you can make with these numbers is 12. Is 12. So this is important. Number is gonna be important right now in order to make the graph. So keep in mind that then we're gonna work with pi 12s. If you remember, the last class was about how to divide the or how to count by pi. By pi fifth, by pi and half. In this case, we're gonna count by pi 12s because the common is the common denominator, the common multiple that these three numbers, these four numbers have. I'm talking about 2, 3, 4, and 6. So keep in mind that number 12. And let's go to Word to see how that works. I'm gonna make a word grid in order to show you the Cartesian plane. Of course, this is a word you can do handwritten yourself because you're gonna do it with cosine. Sine and cosine are very similar. If you remember the list of values of sine and the list of values of cosine practically have the same or consider same values, just that they are in different positions because they are playing different roles. So let's see how it's gonna be the shape of sine in this um, word grid that I create in order to see how is that graph. So here we go, and there's the grid. So maybe you don't see as well, but I'm gonna sum it. Okay, I think now you see better. If you see, if you cannot see, here is 1, here is the square root of 3 over 2, here is square root of 2 over 2, here is 1/2. Those values sound familiar for you? I think so, because they are the ones that we have in here. 0, 1/2, square root of 2 over 2, and a square root of 3 over 2. So it's very important, right now that you remember those values. So that list, it's something you did in homework, so I think you're totally clear why those values are here. So this is what we have, and let's make the analysis or the shape. Let's see how's the shape. I told you that we need to divide or count pi 12s by pi 12s. Why? Because what's the common denominator that the values that work with the unitary circle they have, okay? Is the common denominator they have. So I already have here the list of all the pi 12 values, if you see, until 2 pi. I know here some of them are not simplified, so we're gonna simplify. Pi 12s is already simplified, and I'm doing this because those will be the x values, and these ones we have in here will be your y values you saw here in this PowerPoint presentation. I'm talking about all these set of points we're gonna plot or we're gonna graph right now in this grid. So pay attention in this work because here's where many of you still not totally right. If you see, here is the list of all the values, but they are not simplified. I'm gonna simplify this one. So 2 and 12 both have a half. The half of 2 is 1, so we don't need to write that that 2 over there, and the half of 12 is 6. Both are divisible by 3. If you divide 3 by 3 is 1, you don't need to write that 1 again. And if you divide 12 by 3 is 4. I'm simplifying right now. I think this is something you can do. Here you can simplify 12 by, yes, 12 by 4. So you can divide 12 by 4. 4 divided by 4 is 1. You don't need to write the 1 again. And 12 divided by 4 is 3. 5 over 12 is already simplified. They don't have a common division. I mean, 5 can be divided by 5 by 12. It's just divisible by 2, by 3, by 4, not by 5. So it's already simplified. 6 and 12. Okay. Yes, this can be divided by 6, and 12 divided by 6 is exactly 2. 7 by 12 is already simplified. 8 by 12 can be simplified. They have a half. The half, I mean, they can be divided by 4. It's 2, and 12 divided by 4 is 3. 2 pi thirds. If you see, I'm just simplifying here. 9 pi over 12, both can be divided by 3, or both are divisible by 3. In this case, 9 divided by 3 is 3. 12 divided by 3 is 4. Continuing the counting, here we have 10 over 12. Of course, you can simplify. One way to simplify this very quickly is just write the fraction in your calculator. If the fraction gives you the same, like right now, I'm gonna try 11 over 12. You know how to write this in the calculator. We'll give you again 11 over 12. It means that's already simplified. What happened with 12 over 12 is just pi. So be careful with that one. And that's why I stopped here in 24 by 12, because I know the division of 24 and 12 is gonna give me 2. Don't believe me, do it with your calculator. So I'm gonna do this in the calculator in order to make that quickly. I hope you do the same. So here we have 13 over 12, no. 14 over 12 can be simplified, yes. If it gives you a mixed fraction, write the fraction, don't write a mix. Remember that radians doesn't work like mix. 15 over 12, I think 15 over 12 can be simplified too. And normally this gives you a mixed fraction because you're going more than 1 pi and you're working with improper fractions. So practically, this is something interesting too. So what about 16? Of course, 16 over 12 can be simplified. That's 4 pi thirds. You can do this very quickly with your calculator again. All you have to do is remember how do we work with the fractions. 17 over 12 can't be simplified. What about 18 over 12 is 3 pi and a half. 19 over 12 can't be simplified. But what about 20 over 12? 20 over 12 is 5 pi thirds. And if you see these 5 pi thirds, these 4 pi thirds, these 5 by 4 are values in the unit circle. What about 21 over 12 is 7 pi 4. Some of the values, not some of the values we have in the unitary circle, excepting those that are 12s, because they are not part of the unitary circle, if you remember. What about 22 over 12? Of course, it's 11 pi 6, so we're almost done. And if you see in the unit circle, 11 pi 6 is too close to 2 pi. We're closer to be there. 23 over 12 can't be simplified. And what about that one? 24 over 12. Yeah, it can be simplified and it's just 2 pi. So now we already have these values. I'm going to feed all these values here in this counting in the x-axis, because this counting is the one we need right now in order to make the graph of sine. So here we go with pi 12s, 2 pi 12s, which at the end is just pi 6, 3 pi 12s, which now is just pi 4th, and so on, right? So 1, 2, 3, 4 pi 12, which becomes to be pi thirds, 5 pi 12s, then 6 pi 12, which is pi and a half, and so on. So I'm just gonna fit, oops, Just gonna fit all those points in here. So I'm gonna stop the video right now and I'm gonna finish this very quickly. Okay, now that we already fit all the values in this grid, this Cartesian plane, of course, all these ones are angles and they represent the x values. That's why they are in the x-axis. I was missing the zero, but the zero is always here. If you remember, this point's called the origin and it's over there. So what do we need to do with all these values and these cross? And okay, what we're gonna do at the end is just plot all the list of points we have in here, being careful in and respecting that every time the x goes first and then the y. Okay, and the values of y, if you see, are very similar every time, like we said. Okay, so how this is gonna be? I'm gonna start plotting all those points in here. And the sine of zero, because we're graphing sine function, the sine of zero is zero, okay? Then we go with the sine of, okay, I'm not gonna do sine of pi 12. You can get it in your calculator, but I'm not gonna do it because I'm just gonna concentrate in the ones we have in the coordinate plane, in the unitary circle, sorry, and we're gonna graph it in here, which is sine of pi 6 is gonna be 1.5. So I'm gonna be like in here, graphing all those points. Wow, this moves a lot. Graphing all those points, we're gonna have like a good idea about how is the shape of, in this case, sine. So let's do the same with the other values. And here we go. Now, what is sine of pi fourth? Sine of pi fourth, if you remember, was the square root of 2 over 2, which approximately goes in there. And what was sine of pi thirds? Sine of pi thirds gives you a square root of 3 over 2. And I'm plotting the points, right? Like we have it in the presentation in order to see how's the shape of sine. What happened with 5 pi 12? Okay, 5 pi 12 is not on the list, but pi and a half gives me exactly 1. I think one is that one. Yes, so I think this is wrong. This one goes in here. Yeah. And as I told you, the shape of sine start like going up and then starts like going down. 7 pi 12 is not in the list, so we're gonna work with 2 pi third, which is it's on the list we're working. And I remember that 2 pi thirds gives me same as this one, which is square root of 3 over 2. Don't get confused. This is 1. This one is the square root of 3 over 2. This one is the square root of 2 over 2. So we can move a little bit down. No. So, but it's like that. So what happened with next value? 3 pi fourth. 3 pi 4, if you remember, gives you exactly, again, a square root of 2 over 2, which is in here. So the idea of make all the work, it's conclude how is the shape of sine. Let's see what's next value. It's 5 pi 6. Yes, that's on the list and gives me, I think, 1.5. Here we go. Here it goes. And move a lot, guy. There you are. So 11 pi 12 is not in the list, but if you remember pi gives you exactly 0. So this value is one of the most important right now, because it represents something interesting in math. It's an intercept. And if you see, this is what I was telling you, that the shape of sine, sorry, goes up and then goes down. In the last presentation, in the last class, in the first class, what happened with 11 pi 12s? We don't care about this one because it's not useful right now. But this one, yes, this one is useful. 7 pi 6, yes, it's on the list and gives me negative 1.5, practically the same as this one, just now in a negative way. And if you see following almost the same part, not almost, it's the same part, just that now you're going down. 5 pi 4 gives me negative square root of 2 over 2, which goes in here. I'm gonna assume it is better, I think. Okay, then we're gonna come back. This just to show you how's the procedure to plot, but I think you're totally clear with how and why I'm plotting those points like this. Yes, we're right. Continuing, going very quickly. 4 pi thirds, it's related with this, so there he is. 17 pi 12 is not on the list, but pi and 3 pi and a half gives me -1. And practically this is like the lowest value. This is like the lowest value this function can get. So there's no gonna be another value like this one. Okay, so here you have it. It's a big point. This is another important point too. You have to keep it in mind. It's useful to understand that practically sine will not go down, will not go lower. Okay, so let's see what happened with the rest. And the rest practically will be, it's almost like this, a reflection of this situation that happens here. Working with 5 pi thirds, we're gonna have a point like in here. Working with 7 pi fourths, now we're gonna have the point like over there with negative square root of 2 over 2. With 11 pi 6, we got a -1/2. You can check those values in the unitary circle or the list that I make. And of course, if we go to 2 pi, it's 0 again. So this is what we have, and this essentially makes the shape of sine. All we have to do right now is like join those values. Of course, you can make this exactly clear if you get the values of pi 12 and some values that are less than pi 12, but it's a lot of work. It's not the work you need to do if you're clear that the shape goes like that. If you see, so good, so amazing. And let me tell you something, this just represents one cycle of sine. The graph of sine, it's a shape that goes like that, like I'm moving the mouse right now, and with that movement that never ends, can go to the negative part too. Okay, but let's do better. And I'm gonna do my best, I'm gonna try to conclude how's the shape of sine. I think you're clear with how's the shape of sine, but here it is. An approach, right? I'm not good with this computer, I think. I'm doing my best too. So please, here we go with sine, and I think I'm doing a good job. You can do this handwritten, of course. I'm doing it like that because I want you to understand the ideas, and because this tool is very easy to use. Okay, here it is. Let's see if we can do something interesting with this, like change the shape to see it better. And here you have, okay, a good approach about the sine shape, the sine function. So this is so useful, and that's what I need that you do. Practically the same happens with cosine, just that cosine behaves different. Will not start in here, maybe start there, and the shape goes a little bit different. So I know it's missing tangent, but that's gonna be for our next class. And I hope you do and understand as well these ones. And the next week, we're gonna have a session of Zoom for your doubts, for your questions. And of course, I think you have to be clear. Just let me conclude in here with something interesting, and it's that this shape of sine can continue to the left the same way, just that you're gonna work with negatives, of course, and can continue from 2 pi and so on, because from 2 pi and so on, you're gonna have something like this, very similar. And at the end, this thing with what we have right now is called the basic cycle of sine, and it's just like the first cycle. It's just like the first rotation in the unitary circle. So you can continue rotating, rotating, and rotating as many times you want, and at the end you can. And apologize for what I'm gonna do, but at the end you can have something like this, talking about sine. And these represent many things in physics. Of course, more exactly right now, not like something like that. Yes, if you understand the idea. I mean, just this first part is the first cycle, but then it repeats and it repeats and it repeats many times. That's why the shape of sine can be studied with the first rotation in the unitary circle. So thank you guys for your time. I hope you understand as well these ideas. And in the homework or the investigation of this week, I'm gonna give you or um, suggest to you a video where it's explained something similar like this, the graph of cosine, because that's gonna be your work. Do the graph of cosine. Not necessarily like this, of course. I'm not asking you for computer work because this is too hard to do. It takes me like 3 hours to do something like that. But you can do it handwritten, and that's what I need. You take a picture and send these in a Word document like I asked you in the first video. So guys, thank you a lot for your time, and I hope you understand this content. Again, is missing the graph of tangent. That's gonna be for next class. Bye-bye.